Power system protection is an essential field in electrical engineering focused on safeguarding the stability, reliability, and safety of electrical power systems. It involves the use of devices like protective relays, circuit breakers, and fuses to detect abnormal conditions, such as short circuits, overloads, and ground faults, and to promptly isolate the affected sections to prevent damage and ensure continuous power supply. Protection schemes are designed to operate selectively, ensuring that only the faulted portion of the system is disconnected, thereby minimizing disruptions. They must be reliable, fast, and capable of distinguishing between normal operating conditions and faults. Coordination among protection devices is crucial to ensure that the nearest device to the fault operates first, enhancing overall system stability. Moreover, protection systems are tailored to specific components like generators, transformers, transmission lines, and distribution systems, each with unique protection requirements. Effective power system protection reduces the risk of equipment damage, enhances safety for personnel, and ensures uninterrupted service to consumers. By combining fundamental principles with advanced technologies such as digital relays, synchrophosphors, and wide-area monitoring systems, engineers create robust protection strategies that adapt to the evolving complexities of modern power grids, including the integration of renewable energy sources and the demands of smart grid technologies. This comprehensive approach ensures that power systems can withstand and quickly recover from faults, maintaining a reliable and efficient supply of electricity. Fundamentals of power system protection is a critical aspect of electrical engineering that ensures the safety and reliability of electrical power systems. It involves the detection and isolation of faults to prevent damage to equipment and maintain system stability. Power system protection is the branch of electric power engineering concerned with the principles of design and operation of equipment called protective relays that detects abnormal power system conditions and initiates corrective action as quickly as possible. Faults in power systems can be broadly categorized into short-circuit faults. These occur when there is a direct connection between conductors or between a conductor and the ground. Open-circuit faults. These occur when there is a break in the conductor. Complex faults. These involve combinations of short-circuit and open-circuit conditions. Protective relays are devices that monitor the electrical network and initiate the tripping of circuit breakers when they detect anomalies. They are essential for mitigating damage during faults. Key types of protective relays include overcurrent relays, detect and respond to excessive current flow. Differential relays, compare the current entering and leaving a section of the system to detect faults. Distance relays, measure the impedance of a line to detect faults based on their distance. Circuit breakers are crucial for automatically disconnecting the faulted part of the system, ensuring the stability and safety of the remaining electrical grid. They operate in conjunction with protective relays to isolate faults quickly. Functional requirements. Protection systems must meet several functional requirements to be effective. Reliability. The system must operate correctly for all faults for which it is designed. Selectivity. The system must isolate only the faulted section without affecting the rest of the system. Sensitivity. The system must detect even small faults. Speed. The system must respond quickly to minimize damage. Coordination involves ensuring that the protection system operates in a coordinated manner with other protection systems to avoid unnecessary tripping and to isolate only the faulted section. For engineers looking to master power system protection, it's essential to delve deeper into the following areas: numerical relays and algorithms, understanding the advanced algorithms used in modern numerical relays. Instrument transformers, learning about current and voltage transformers and their role in protection systems. Protection schemes, exploring various protection schemes such as differential protection, distance protection, and overcurrent protection. Substation automation, understanding the role of automation in enhancing the reliability and efficiency of power systems. Renewable energy integration, addressing the challenges and solutions for integrating renewable energy sources into the power grid. By mastering these concepts, engineers can design and implement robust protection systems that ensure the reliability and safety of electrical power systems. Components of protection systems: current transformers CTs and voltage transformers VTs. Current transformers CTs used to measure high currents by producing a reduced current proportional to the current in the circuit, which can be safely monitored and measured by protection devices. Voltage transformers VTs used to step down high voltages to lower levels for metering and protection purposes. Circuit breakers play a critical role in isolating faulted sections from the healthy parts of the power system. They operate based on signals from protective relays and can interrupt current flow to prevent damage and ensure safety. Protection relays analyze power system parameters like voltage, current, and frequency. They send trip signals to circuit breakers when they detect anomalies, ensuring rapid fault isolation. Relay coordination ensures that only the closest relay to the fault operates, isolating the faulted section and maintaining service continuity elsewhere. Coordination is achieved using time delay settings and selectivity principles. Selectivity: this ensures that protective devices operate selectively so that only the faulted part is isolated, minimizing disruption to the rest of the system. Protection schemes: overcurrent protection uses overcurrent relays to protect against excessive current that can damage equipment. This is the most basic form of protection. Differential protection compares the current entering and leaving a protected zone. Any difference indicates a fault within that zone. Commonly used for transformers, generators, and bus bars. Distance protection measures impedance to locate faults on transmission lines. Relays calculate the distance to the fault based on voltage and current measurements. Advanced protection concepts: directional relays, used to detect the direction of fault current. Essential for protecting interconnected networks where fault current direction can vary. Adaptive protection adjusts protection settings in real time based on operating conditions and network configurations to enhance reliability. Wide Area Monitoring Systems (WAMS) use phasor measurement units (PMUs) to provide a wide area view of the power system for better situational awareness and faster fault detection. IEC 61850, a standard for substation automation that facilitates communication between devices using a common protocol, enhancing interoperability and efficiency. Renewable energy integration, inverter-based resources (IBRs), as renewable energy sources like solar and wind are integrated into the grid. Protection schemes must adapt to the different fault characteristics of inverter-based resources compared to traditional synchronous machines. Microgrids, small-scale power systems that can operate independently or in conjunction with the main grid. Protection schemes for microgrids must handle frequent transitions between grid-connected and island modes. Testing and maintenance, routine testing, regular testing of protective relays, CTs, VTs, and circuit breakers to ensure they function correctly. Predictive maintenance, using data analytics to predict equipment failures before they occur, allowing for proactive maintenance and minimizing downtime. Human factors in protection systems, training and education. Continuous training for engineers and technicians is crucial for the effective operation and maintenance of protection systems. HMI Human-Machine Interface, user-friendly interfaces for monitoring and controlling protection systems, ensuring that operators can quickly understand and respond to system events. By thoroughly understanding these fundamentals and advanced concepts, engineers can design, implement, and maintain robust power system protection schemes that enhance the reliability and safety of electrical power systems. Fault analysis, understanding faults and their impacts on power systems is crucial for designing effective protection schemes. Types of faults: symmetrical faults. These involve all three phases equally and are rare but severe, such as three-phase short circuits. Asymmetrical faults. These are more common and include single-phase to ground, phase-to-phase, and double-phase to ground faults. Fault currents are significantly higher than normal operating currents. Accurate calculation of these currents is essential for setting protection devices. Protection zones. A power system is divided into several protection zones to localize faults and minimize disruption. Each zone is protected independently. Generator differential protection protects against internal faults by comparing the current entering and leaving the generator. Overvoltage protection safeguards generators against voltage spikes. Loss of excitation protection detects loss of field excitation in generators, which can lead to instability. Transformer protection, differential protection, detects internal transformer faults by comparing input and output currents. Buchholz relay, mechanical relay used for detecting gas accumulation or oil movement inside transformers, indicating internal faults. Overcurrent and earth fault protection provides backup protection against external faults. Transmission line protection, distance protection, uses impedance measurement to detect and locate faults along transmission lines. Pilot protection schemes employ communication channels between relays at both ends of the line for fast fault detection and isolation. Overcurrent protection provides backup protection for transmission lines. Distribution system protection, feeder protection, uses overcurrent and earth fault relays to protect distribution feeders. Reclusers and sectionalizers automatically restore